Hi there. So in this lecture, we'll start looking at the solutions to the mutual exclusion problem in the distributed setting. So once again, before solving any problem, you need to make sure that you know what the system model is under which you're solving the problem. So here are the assumptions in our system model here. Each pair of processes that is connected by reliable channels, which means that when you send messages on these channels, they are delivered eventually. We can use TCP for these channels. The channels are all point-to-point channels, which means that they have one sender and one receiver. Messages along a channel are delivered eventually to the recipient, and they're delivered in first in, first out order, which means that if one message is sent before the second message, then the first message is received before the second message as well. And finally, we'll assume that processes do not fail. There are many variants of the algorithms that we'll discuss, all the algorithms that we'll discuss that are fault-tolerant variants, and these are present in the literature. So our first solution is a central solution. This uses a central master or a leader, which is elected using one of our leader election algorithms that you have seen elsewhere in the course. The master keeps a queue of waiting requests from processes who wish to enter the critical section. The master also has a special message called the token message. Access to the token message allows the holder to access the critical section. So the token message is a very special message. It's like cash. If you have it, then you can use it, whether you're a good person or whether you're a thief. So when a process wants to access the critical section, it calls the enter function, where it sends a request to the master, and then it just waits in a loop for the token from the master. When the process receives a token, it enters the critical section and hangs on to the token. When it's done with the critical section, it calls the exit function, wherein it simply sends a token back to the master. What data structures does the master maintain, and what does it do? Well, when the master receives a request from a process PI, if the master currently has the token, it simply sends a token to PI, which gives PI access to the critical section. If the master does not have the token, this means that some other process has the token, and in this case, the master ends up queuing the PI request alongside other requests that may also be waiting. When the other process that has access to the critical section releases the token, this token is received back at the master, and the master then looks at its queue. If the queue is not empty, it takes the head of the queue, some process PJ whose request was sent and queued there, and this process PJ is then sent the token, which gives it access. Okay. Notice that this process PJ's request will be removed from the queue after it's sent the token. However, if the queue is empty, this means that there are no outstanding requests, and the master can then hang on to the token at this point of time. So let's analyze this algorithm. So why does this algorithm guarantee safety? It guarantees safety because it is exactly one token, and only access to the token gets you access to the critical section. Why does it guarantee liveness? Liveness is guaranteed if every request is granted eventually. This is guaranteed because there are at most n processes in the system, and so if your request is queued at the master, there's going to be at most n-1 requests ahead of you. So when each of these requests finishes, because there are no failures, and eventually when your turn comes at the head of the queue, you will get access to the token and the critical section. The ordering guaranteed here is FIFO in the order received at the master. So if your request came in slightly earlier than your friend's request at the master, then you will get access to the critical section just before your friend's request. So those are correctness properties. What about performance properties? There are two requirements from mutual exclusion algorithms. One is that they involve few messages, which means that they're incurring lower overhead on the network itself. And second is that they incur low delays at the clients that access the critical section. This means that the overhead of accessing critical sections and releasing them is fairly low. There are three metrics that capture these. The first is bandwidth, which is simply the total number of messages sent in the enter and exit functions. The client delay and synchronization delay are as follows. The client delay is a delay incurred by a process when there is currently no other process in the critical section. Okay? Which means that right now there is no one in the critical section. One process comes along and says, hey, I need access to the critical section. How long does it take that process to get into the critical section? The synchronization delay is the delay between one process releasing the critical section, that is calling the exit function, and the next waiting process getting access to the critical section. Okay, so we assume that there is only one releasing process, and there is only one waiting process for the synchronization delay. So let's analyze the central algorithm for these. Bandwidth, once again, for the enter operation only involves the requesting process sending a request to the master, and it receives a token back. So that's 2 total messages, no matter when these messages happen, but that's 2 total messages. For the exit, the requesting process or the process in the critical section simply sends a token back to the master, so that's 1 message for the exit. For the client delay, the master has a token because there is no one in the critical section, and the requesting process sends a request to the master, which sends it back the token, so that's 2 message latencies or 1 round trip time. Synchronization delay, the process in the critical section exits the critical section by sending the token to the master, so that's 1 message transmission. Then the master sends the token forward to the next process in the queue, which is another message transmission, so that's 2 message latencies for the synchronization delay in the central algorithm. So the master, of course, here is the performance bottleneck because it could get overloaded with a lot of requests, and also if the master fails, then you have a single point of failure, which means that until a new master is elected, you cannot serve any more mutual exclusion requests. So our next algorithm tries to address this by eliminating the master altogether and instead using a ring. Here we organize all the processes in the system into a virtual ring, where each process can talk to its successor in the ring. Typically, this is a clockwise successor. So for instance, N3 is a process, its successor is N32. It can send messages to N32. N32 is another process in the ring, which can then send messages to its successor N5, and so on and so forth, and the ring loops around. We have a special message called the token message, shown as a blue message here on the slide. The process that has the token message at any point of time can enter the critical section. No other process can enter the critical section. So N3 currently has access to the critical section. It, if it chooses so, can access the critical section at this point of time. When it's done, it can pass on the token to its successor in the ring. At this point of time, no one can access the critical section anywhere in the group because the token is in transit, it's on the network. When N32 receives the token, it can then access the critical section. If it's not interested, it simply passes on the token to its successor. So once again, we have N processes in a virtual ring. Each process can send a message to its successor in the ring. There is exactly 1 token in the ring. In order to enter a critical section, you simply wait until you get the token. There is nothing you can do to actively seek out the token. When you're done with the critical, when you're in the critical section, you hang on to the token. When you're done with the critical section, you simply pass on the token to your successor in the ring. If you get the token and you're not interested in the critical section, meaning that you're not in the enter function, then you simply pass on the token immediately to your successor in the ring. So why does this guarantee safety? Well, there is exactly 1 token, and for the same reasons as in the central mutual exclusion algorithm, safety is guaranteed here. Liveness is guaranteed because there is a finite number of processes in the ring, and the token eventually loops around and reaches the requesting process. This, of course, assumes no failures, which means that the token is not lost and that the ring stays intact. Bandwidth per enter operation, there is only 1 token message received by the requesting process. However, the other n-1 processes might have to put an effort in transmitting the token around. So the total number of messages per request might be as high as n throughout the system. There is, of course, just 1 message per exit operation where the process passes on the token to its successor in the ring. What about performance? Let's look at client delay. Client delay means that there is currently no one in the critical section, and suddenly 1 process comes up and says, aha, I need access to the critical section. The best case is when this process already has access to the token, in which case the number of message transmissions is 0. The worst case is when this process that just requested access to the critical section has just passed on the token to its neighbor or to its successor. In this case, the token now needs to make its way around the other n-1 processes, because in a system of n processes in a ring, you have n links. This means n message transmissions for the token to come around, and that's the worst case. So the client delay could be anywhere between 0 to n message transmissions. What about synchronization delay? Synchronization delay means that 1 process releases the token and 1 other process somewhere in the ring is waiting for the token. The best case is just 1 message transmission where the waiting process is the successor of the releasing process, which means that the token makes only 1 hop before it gives access to the critical section. The worst case is when the process that is waiting is the predecessor of the process that is releasing the token. In this case, the token needs to make its way around the ring in the clockwise manner to reach the requesting process. And that's n minus 1 message transmissions in a system of n processes in the ring. Okay, so the synchronization delay could be anywhere between 1 to n minus 1 message transmissions. So we solved somewhat the bottleneck problem with the central mutual exclusion algorithm, but the client delay and the synchronization delay have gone up to be order n in the ring-based approach. The question is, can we do better than this? Can we lower this client and synchronization delay further? And the answer we'll see in the next lecture.